Hello, class. Good afternoon. I'm going to call the roll. First lay is the 903 section 903. Raise is Raise here.
Here.
Oh, thank you. Jackson, Jessica. Let's see. Jessica is here. Emma is here. Jack is here. Okay. Jessica is here. Molly, is Molly here? Hi, Molly. Avery, is Avery here? Let's see. Alex is here. Avery, I do not see her. Okay, absent. Cindy. Cindy is not here. This is section 903. Now I'm gonna record attendance for section 904. Emerson.
Here.
Oh, thank you. Did I pronounce your name right?
Yes.
Your name is Emerson Dan, right?
Emerson works fine.
Oh, okay, awesome. And Alex, I think I see Alex. Yeah. Alex is here. Lexi. Lexi is here. Very good. Excuse me. Emma is here. Ashlyn, I think I saw is here. Very good. Thank you. Jack is here. Zayn. We don't have Z here. Absent. Close this one. Angie. Yeah, Angie is here.
I am here. I am here.
Awesome. Very good. Perfect. Angie's here.
Yes.
Jennifer. Jennifer is here. Crystal is here. Very good. Charlie. Charlie Scott. No. Charlie's absent. Chloe is here. Levy is here. Awesome. Very good. Let me save 2 absences. Perfect. Thank you guys for coming. Based on the syllabus, today we are going to cover section 1.2. What do we learn in section 1.2? Estimation. All right, I'm going to show you my table note for this section. What is estimation? Estimation refers to a process of getting an approximate answer to a question. Why do we need an estimate? Sometimes we need an estimate for convenience. For example, if we have a very large number, let's say we have number 1, 2, 3, 9, 8, 7, 5, 4, 3. Let's say we have a very large number. This is 123,987,543, right? It's a very large number. And it has details in it. It's not convenient to remember exact the value equal to. So we want to use the estimation to approximate the value. If I want you to help me to round this number.
Miss Betty,
Yeah?
it's a student that says she can't hear you talking.
Oh, sorry, I did not check the chat. Molly, so do you guys, do other students hear me? I believe you hear me, right?
Yes.
The other students can hear me. I believe it's an issue on your end. Maybe try to log out and log in back. Okay, awesome. So where was I? Okay, yeah. So please help me to round this number to the nearest million. You know, it's gonna be convenient if we round the number to the nearest million. How do we do it? If we are about to round this number to the nearest million, then the place the rounding is going to occur is here, right? So this is ones. This is tens. This is hundred. This is thousand. This is 10,000. This is 100,000. And right here is million, right? So we need to round this number to the nearest million. So 3 there, that's the place the rounding is going to take place. To round a number to the nearest million, we look at the digit right behind it. Right behind 3, we have a digit 9. Since 9 is bigger than or equal to 5, we are going to round this number up. Round it up. We are going to add a 1 on top of 3. And this number can be rounded to 124 million. Instead of refer to this number as 123,987,543, we can say this number is about equal to 124 million. Isn't that more convenient, guys? Please let me know, is that clear? Okay, thank you, Jack. Thank you, Levy. How about you help me to round, let's exercise more for this number. Can you help me to round the number to the nearest 100 million? Okay? Help me to round this number to the nearest 100 million. Firstly, find the rounding place. Yeah, let me write the number again. 123,987,543. We need to round this number to the nearest 100 million. So firstly, find the rounding space, rounding spot, and then look at the number behind it. If the digit behind it is less than 5, we round it down. Otherwise, if the digit behind the rounding place is bigger than or equal to 5, we round it up. Please share an answer in the chat. 100 million, exactly. Thank you, Jack. Thank you, Jennifer, Cindy, Ashley. You guys are great. Crystal, those are correct answers. And if we say the numbers around equal to 100 million, that is also very convenient, right? The rounding place is here. This is a million, this is 10 million, so this is 100 million. And the digit behind it is 2. 2 is less than 5, so we round it down. We round it down, round this number down to 100 million. Okay, so that's one reason. Sometimes we need a estimate just to make the number more convenient to refer to, right? For the convenience. Sometimes, some other times, we need an estimate. We have to estimate because the exact number is not possible to have. Okay, yeah. Another reason for estimation is sometimes it is not possible to get the exact answer. For example, pi. We all know what is pi, right? Pi is the most famous irrational number. It is an irrational number, means this number is a non-repeating, non-terminating decimal. It is equal to, and so on and so on and so on. 3.141596. That's how many digits I remember. Some genius, they know the 100 digits behind the decimal point. Kind of cool, right? But I don't really know the point. So since this number is irrational, it is a non-repeating, non-terminating decimal, means the digit continue forever. Not just continue forever, there's no pattern. You don't know. It's just irrational. Exactly like the name shows, like a crazy decimal. So it's not possible for us to know the exact value. In this case, we have to estimate. Okay, this is decimal. So what if we wanna round this number, estimate this number to round it to the nearest hundredth? Round pi to the nearest hundredth. Okay, it's different from 100. It has a th following d. So this is hundredth. I want to show you quickly on the guided note. There's a chart can help you to understand the names for each place value. So this is decimal point, right? Right behind decimal point, that is a tenth, and then hundredth, and then 1,000th, and so on. So if we want to round a pi to the nearest hundredth, how many decimal places should we keep? Or where is the rounding place? Hundredth. As long as it has a th, means the rounding place is going to occur in a decimal part to the right of the decimal point. Anybody would share where is the hundredth? It's kind of funny for me to pronounce it. Hundredth, right? Perfect. It is a 4. Thank you, Molly. I believe you hear me right now. Perfect. The problem is fixed. Thank you, Alex, Molly, Ashton, Crystal. Emma, what is? Oh, it's typo, I believe. Yeah, it is. Yeah, it is a 4 exactly. This is the rounding place. Okay, this is a tenth. Okay, and this is a hundredth. So we are going to round this number to keep 2 decimal places. Since the digit behind 4 is less than 5, we're going to round it down, and we can round a pi as 3.14, and that's the value we should be pretty familiar with 3.14, right? That's the best. That's the most common used estimation for pi. What if I want you to help me to round a pi to the nearest, let's see, 10,000. Okay? What if I want you to help me to run the pi to the nearest 10,000th? How many decimal places should we keep? And you can type your final answer. What do you have? So, yes, exactly. Perfect. This is the 10,000th place value. Okay, very good. Since the digit behind it is bigger than 5, is 9 bigger than 5, bigger than or equal to 5, we're going to run it up. Run it up to 3.1416, right? So this is how we run it up. Since 9 is bigger than or equal to 5, so we run it up. When we run it up, we need to add a 1 on top of the value in the rounding place. It was 5, now it's going to be 6. So the estimation is 3.1416. Perfect, awesome. All right, so we gave 2 examples while considering the reason we estimate. The reason we estimate. How to estimate? So 2 things in this section. The first thing is rounding. We already practiced, right? The first question, how to round a whole number. The second question, I use pi as the example, and then we practice the rounding a decimal, right? Another thing of this section that's a more challenging thing is the mathematical model. In mathematics, we use modeling, the technique of modeling to estimate some real world situation. So I'm going to go ahead show you the question in a guided note. The last question. We're going to work on this problem, okay? I'm going to modify this problem a little bit. Find the equation that model the linear trend. And part C, we're going to predict. All right, let's see what we have in this example. Sometimes I go straight to look at the information in a graph. Most of the time, I am able to get all the information simply just from the graph. Then I do not have to spend time to read the words, right? That's one way to do it. So this graph is a multi-bar graph. Knowing bar graph is different from histogram. Well, you don't have to really worry about that if you don't know what is a histogram. Just to know, bar graphs have those bars separate. There are gaps between the bars. This is a multi-bar graphs. Multi-bar graphs are good at comparing information. As you can see, we have red bars, we have yellow bars. The red bars represent the males, right? If you look at the vertical scale, life expectancy, the height of those red bars represent the life expectancy for males. And the yellow bars, the height of the yellow bars, the number above those yellow bars, they are the life expectancies for female, for female. And the horizontal scale represents time. As you can see, we have a 1950 as the beginning, and 1960 all the way to 2020, right? So the horizontal scale represents the birth year of the subjects, and vertical scale represents those subjects' life expectancy. Red bars represent male, yellow bar represent the female. It's interesting that to see in general, statistically, female live longer than male, right? Kind of interesting thing. So as you can see, in 1950, the average life expectancy for a male is 65.6-year-old. For female is 71.1-year-old, and so on and so on. So that's how you understand the graph here. We have 3 parts to complete. Let's look at the requirement for part A. A man's increased life expectancy rounded to the nearest hundredth of a year for each subsequent birth year. Some questions make the understanding a little bit challenging. I would say for part A, read the requirement more times. What are we looking for? In part A, we are looking for a male's increased life expectancy for each subsequent birth year. Put it in short, we are looking for the increased life expectancy for male every year, or yearly or annual increase. We are looking for annual increase in life expectancy of male, right? Do you agree, guys? So part A, we are looking for the annual or yearly increase in life expectancy of males. Do you agree? Do you agree that's what are we looking for in part A? Since it only mentioned male, I think we can just ignore the yellow bars. Only look at the red bars. Look at the red bars. Look at the red bars. There is a linear increasing pattern, right? There's a linear increasing pattern. So from 1950 to 2020, the life expectancy for males has increased. Okay, has increased. Has increased how much? In 1950, the life expectancy is 65.6, and then go up, go up, go up, go up. So by the year of 2020, the life expectancy for males is 77.1. So over, that's how many years? From 1950 to 2020. From 1950 to 2020. How many years that is, guys? From 1950 to 2020. How many years that is? 70 years, exactly, perfect, exactly. So over the 70 years, over the 70 years, the total increase in the life expectancy of male is 77.1 minus 65.6, right? It is consistently going up. In 1950, the life expectancy is 65.6. By the year of 2020, it has increased to 77.1. So over the 70 years, the increased amount is 77.1 minus 65.6. It is 11.5. 11.5. How do I understand this number 11.5? You know, this course is a quantitative reasoning. We really need to focus on understanding or make sense of the numbers. We don't really do much algebra, by the way. It's really makes more about making sense of the number. So this means from 1950 to 2020, over the 70 years, the life expectancy for male has gone up 11.5 years, 11.5 years, right? But that increase, 11.5 years, is over the 70 years. Then how do we find the average yearly increase in the life expectancy of male? This increase, by the way, again, it is the increase over the 70 years, but we are not looking for the total increase over the 70 years. We are looking for the average yearly increase. What should we do? Divided by 70. I believe, Jennifer, you mean divide 11.5 by 70, right? 11.5 is the total increase. Perfect. Is the total increase over the 70 years. So the average yearly increase would be divide the total amount by the number of years, by 70, right? Okay, let's see what do we have. Does that make sense, everybody? Let's say you have a toddler or a child that is in the phase of like growing fastest time period, and let's say over 10 years, your children, 10 years too much, over 5 years, your son has grown 3 feet. Okay, yeah, over the 5 years, let's say you have teenager son, over the 5 years, he has grown 3 feet taller, right, than 5 years ago. Then, averagely speaking, his average yearly growth, you use the 3 feet to divide by 5, right? So that is 0.6 feet. Does that make sense? Okay, so similar with that. So let me divide 11.5 by 70. I have this number. So for part A, we use 77.1 minus 65.6, and then divided by 2020 minus 1950. Numerator is the total increase in the life expectancy of male. It is 11.5 years. Denominator is how many years from 1950 to 2020. So over the 70 years, the increase is 11.5, and the quotient is 0.16428571. This actually is approximate because my calculator doesn't have enough space to contain all the digits. But we need a round number anyway, right? The question requires us to round the number to the nearest hundredth. Okay, guys, after we round the number to the nearest hundredth, what's the result supposed to be? Hundredth. Yeah, do we keep 2 decimal places? Perfect, exactly. You guys are great. We keep 2 decimal places. Since 4, the digit behind the rounding place is less than 5, we round it down. So we have 0.16. That means from 1950 to 2020, over the 70 years, the average yearly increase in the life expectancy of males is 0.16 year. Not very clear about what is 0.16 year, right? So let me multiply 0.16 by 12 months. That is 1.92 months, so shy 2 months. So over the 70 years, averagely speaking, every shy 2 months, hold on. Oh no, my bad. So it's just the 0.16. Yeah, it is shy 2 months, around 2 months. So every year, the life expectancy of males has been increasing. Every year, the life expectancy increased by a little bit less than 2 months. All right, guys, does that make sense? Let me summarize. For this type of problem, if you see the bars has a linear trend, what does that mean when we say linear trend? Means the trend can be described by a straight line, as the straight line, the black straight line I draw here, right? Pretty well match the trend of the red bars, right? And how do you find the yearly change in Y? Y here is the life expectancy. All you need to do is this, okay? You use the number on top of the tallest bar minus the number on top of the lowest bar. Use that difference to divide by the number of years. How do you find the number of years? You use the ending year to minus the beginning year. And that's all you need to do. If you are familiar with what you have learned in Algebra Foundation 2, maybe some of you have already identified this value. We got around equal to 0.16 year. That value, in fact, is the slope of the straight line. Okay, is the slope of the straight line. Rise over run. Rise over run. The rise is 77.1 minus 65.6, right? Rise over run. Run is the 70 years. It is actually rise over run, so it is the slope. It is the slope of the line that fits the linear trend. Okay, make it simple for us to find the answer for part A. If it's to find the yearly change in variable y, you just need to use the number on top of the tallest bar to minus the number on top of the lowest bar, and use that difference to divide by the number of years, and that's it. Okay, don't worry if this time you don't completely understand it. After this example, you will have a chance to practice on your own. We're gonna figure this out, right? Because estimation is not that fancy, especially roundings, kind of like you probably already learned that from elementary school. The challenging part is the modeling part. Okay, let's see if you have any questions here. Okay, seem fine. Okay. By the way, if you missed the attendance taking, remember to email me. Then I can fix your attendance. Otherwise, your grade will be compromised. So if you are late and you missed the beginning of the class, you need to remember to email me and let me know you are here. You attended the class. All right, that's the part A of this question. Part A of this question. Part B. Part B of this question is we need to find the equation of the line that describes the linear trend of those red bars. I draw the line for you, right? If you have a chance to take statistics, and you would know there exists a straight line that best fit the linear trend. There's a standard criteria to evaluate this straight line is the best fit, better than the other straight line. So suppose the best fit straight line is this black straight line I have here. We want to find the equation for the straight line. Straight line is a graphical or geometric concept. So in order to study it use algebra, we have to translate that to an algebraic expression. So that's the equation that represents this straight line. This also takes the knowledge from your Algebra Foundation 2, okay? Algebra Foundation 2. Do you remember this formula? Y equals mx plus b. I hope it is familiar, looks familiar to you. And this formula is very famous. It is the slope intercept form of a straight line. All right. On the left side of the equation, we have a variable y. On the right side of the equation, we have two parts adding together. The first part is m times x. M here is the slope. M here is the slope. The slope of the line. And the second part on the right, B here is the y-intercept, okay? Y-intercept. It might help if you can write this down. It would help you to understand the linear modeling better. Y equals mx plus b. So this is the equation for a straight line that describes the linear trend of those bars. M here is the slope. It is also the rate of change of y. B here is the y-intercept. It is also the initial value of y. Okay? Y here in our example is the life expectancy. Okay? X here is the number of years. So let's say this equation y equals mx plus b corresponds to this black straight line. And we need to find the equation, right? In order to find the equation, we need to know the values for m and b. Now, how do we find the values for m and b? Let me make this simple for you. For part B, in order to find the equation of the line that fits the linear trend, we need to find the value of m and the value of b, right? Okay, this is how do we do it. The value of m is the answer from part A. M here is the slope, rise over run, right? Is the, specifically for this example, is the yearly increase in the life expectancy. Yearly increase in y. Y always represents the vertical scale. So M here is just the answer you got from part A, which is 0.16. And how do we find the value of B? Think about the trend start from 1950, right? So that means the problem sees 1950 as the initial years. 1950 here is the initial year, the very beginning, initial year. So B value is going to be the life expectancy at the very beginning or in the initial year. Okay, is the number on top of the shortest bar, 65.6. 65.6. And that's it. This equation is the model. Describes the linear trend of those red bars. And let me repeat the key information here. Part B, we need to find the equation for the line, right? We need to know the value for the slope, and then we need to know the value for B. Slope is just the answer you got from part A, the yearly increase in the life expectancy of males. B here, the constant, is just the life expectancy in the initial year. In this case, is in 1950. So it's the value on top of the shortest bar, 65.6. Because if you let x be 0, y equals 65.6, right? So the very beginning, the life expectancy for male is 65.6. This also shows you that x here is the number of years after 1950. Okay, x is not a specific year. X here is the number of years after 1950. So when a year is 1950, x is 0, right? X equals 0. Because in 1950, the year after 1950 is just 0. And when the year is 1951, x equals 1, right? And so on. And when y equals, let's say, 2020, x should be equal to 70, right? That is 70 years after 1950. So understand the connection between x and y. The capital Y, sorry, capital Y. Capital Y is a year. How does x represent the time? How does the x represent the time? All right, x here again is the number of years after 1950, because we see 1950 as the beginning, as the initial year. Well, I said a lot. Simply put, M here is your answer from part A. B here is the number on top of the shortest bar, or the beginning, at the beginning. Any questions, guys? Okay. Oh, that's my own message. Do you guys have any questions about part B? Oh, good. Perfect. Thank you, Ashley. We have 16 participants. This is a very big class. All right. I think I'm all good. Thank you, Crystal. Thank you for your response. Excuse me. One more part. So in part C, we are going to use the model we found in part B to predict. Prediction is one of the main purposes we need to do modeling. Okay. If we look at the trend, the straight line, if we assume the trend continue, then we should be able to predict the life expectancy in the future, right? Yeah, suppose the trend continue, we should be able to know the value of the life expectancy for males in the future. So that's advantage about modeling. So I don't know how many of you are familiar with the stock market. You know, the professional, they have very fancy software. How do those softwares work? is actually modeling. So let's suppose this is the trend of the price of the stock, right? And they look at a pattern and they find the equation. This is not linear, obviously, right? It's more complicated, maybe polynomial or even more complicated functions. So they find the equation like what we did just now. Our equation is a straight line, right? But this is maybe not some other type of curves. And they assume the trend continues. They assume the trend continues in the next minute or even next 10 seconds. Then they would be able to predict the price of the stock in the next 10 seconds. And then they do the trade. They trade it. So that's how the software actually works. That's the idea behind it. And our modeling is pretty a lot simpler. It's just a straight line. Let's see, how do we use our linear model here to predict the life expectancy of a male born in 2030. Okay, the year here is in the future. Year 2030. We don't know, right? From the given information, we don't know because those information are from the past. 2030 is in the future. Even now, even the book is a 2021 version. Yeah, 2030 is still in the future. So we can only predict. How do we predict? We find a model. We didn't find our model. We found a very good model. It's a linear model. So we are going to use the linear model to predict the life expectancy of a male born in 2030. Okay. All right, let's see. Let me write our model one more time right here. This is our model. Y equals 0.16x plus 65.6. This is our model. We got it from part B. What is x here? I already wrote it here. X here is the number of years after 1950. What about y? Y here is the life expectancy for a man. Okay, so since we are predicting the life expectancy for a man born in 2030, we are predicting the value for y. Okay, we are predicting the value for y. Based on the model, in order to know the value of y, we have to know the value of x. Okay, so what's the value of x? We can plug in to find the value of y. That represents the life expectancy of a man born in 2030. What do you think? We have to know the value of x in order to calculate for y, right? Should we just plug in x equals 2030? Should we just plug in x equals 2030? You guys are great. That means no, right? We don't. Yeah, you are right. It's 80. Perfect. You guys are great. So in 2020, in year of 2020, x equals 70. So in year of 2030, x is 80. Okay, x in the model, x here in the model is not the year. It is the number of years after 1950. So 2030 is 80 years after 1950. So x should be 80, not 2030, okay? Yeah, you guys are great. We do not plug in x equals 2030. We should just plug in x equals 80. Plug in x equals 80. Let's see what we have. Then y equals 0.16 times 80, and then add 65.6. I believe you can do the algebra here, right? Just use a calculator. 0.16 times 80, 12.8. and add that on top of 65.6. 65.6. We have 78.4. So that sounds great, right? That means in the future, statistically, averagely speaking, if a male is born in 2030, his life expectancy is 78.4-year-old. That sounds very good, right? Maybe it's your children, your future children, or your future grandchildren, right? If the trend continues, that's the assumption. So this actually means perfect sense. This means perfect sense. Let me explain here. If you think about every year, yearly increase is 0.16. Yearly increase, start from 1950, yearly increase is 0.16. And if the trend continue for 80 years, all the way to in the future 2030, then the total increase would be 0.16 times 80, 12.8, right? Add that on top of the life expectancy in the initial year, and we have the predicted life expectancy in 2030. All right, guys, do you have any questions about this example? It took quite a while for us to cover the 3 parts, right? How about let me summarize before we move away from this example. This problem is about a linear modeling problem. Okay, linear modeling problem. Firstly, you would be given a bar graph. The bar has a linear trend going up or going down. This one is going up. If it's going up, to find the part A, the yearly change in Y, you just need to use the number on top of the tallest bar minus the number on top of the shortest bar, and use that to divide by number of years. To find the number of years, you just need to use the ending years minus the initial year. In other words, you are actually looking for rise over run. That's the slope of the black line. Part B would require you to find the equation for the linear model. We use the slope-intercept form of the straight line. And how do we find the value of m and b? M, the slope, is the answer from your part A. B is the number on top of the initial year. And that's how you have the model. Once you have the model, you can predict the value of y for the year in the future. So you need to find the value of x that corresponds to the year in the future. Like in this example, we are looking for the life expectancy of a man born in 2030, but you don't plug in x equals 2030, you plug in x equals 80. X here is the number of years after 1950. So that's the whole package for this type of problem. Since in the past semesters, this question is seems the most challenging problem. Yeah, students always have to ask the problem, and you also have a few similar problems in MyLab Math. So we spend time to talk about it in a class, and it's kind of important. A linear modeling is a very important way to estimate a real life situation, right? Think about the example I gave you for the stock market is very interesting. Simulation, something like that. Okay, are you ready to practice on your own? Let's go to our Pearson. Let's go to 1.2. Let's look at question. Let's look at question 22. Yeah. All right. Please work on this problem. We work on problems as a team in the class. I know you see a similar problem on your end, on your in your MATLAB math, but the numbers might be different. Instead of working on your problem, um, you know, and missing the information from the class, I'd like you to just focus on solving this problem. If you understand the problem, you'll be able to know how to solve it on your own for your problem, right? So let's see what's going on in this problem. This is about the average global temperature in Fahrenheit. The x-axis gives the years, 1950, 60, 70, all the way to 2015. On top of the bar, we have the numbers. Those numbers are degree of the temperature in Fahrenheit. So my understanding is this is a global warming example. It shows you the trend, right? Well, you might argue this is not straight line. We only learn linear model. We don't learn, more complicated model. So since it is increasing, as you can see, continually increasing, right? We are going to use a straight line, a linear model to describe this situation. Again, we are estimating, right? We are not finding the exact, we are just estimating. So since it is a going up trend, as you can see, every time go up, go up, go up, go up, right? Even it is a curve, but we can use a straight line to estimate it. Okay, yeah, we are just estimating. Okay, it is very similar with the problem we just had. It has three parts here, guys. First part, you have 2 minutes. Now is 57. I'm gonna check on you in 2 minutes. Part A, you need to find the yearly increase in the average global temperature per year. Okay, I'll give you 2 minutes. If you have no idea how to do it, look at the example we just did. Hmm? We are using a linear model to estimate the trend. This trend, right? Let me do it better. Okay, so part A. What is your answer, guys? Well, I need to work on the numbers to see what do we have, okay? So remember, we are looking for yearly increase in the temperature, right? Yearly increase in the temperature. So how about let's find the total increase first. From 1950 to 2015, the temperature goes from 56.94 to 57.88. All right, from 1950 to 2015. So over the, I think that is 65 years, right? From 1950 to 2015, over the 65 years, the temperature has gone up. Let me see how many degrees it has gone up. We use 57.88 minus 56.94, 0.94, right? Yeah, let me double check. Minus 56.94. Yeah, and then yeah, so that means over the 65 years, the temperature has gone up 0.94 Fahrenheit, and divide that by 65. I have 0.01446,154, and we need to round this to the. Let's see what's the rounding requirement. When you work on the assignment in Pearson, you need to pay very attention. Yeah, pay very attention to the rounding requirement in the parentheses. It says to round the nearest hundredth. So keep two decimal places, right? So it's gonna be 0.01. Round it down. Do you have 0.01, guys? Yeah, you guys doing great. 0.01. Yeah. Yeah. The reason we run it down because the 4 here is less than 5, right? Suppose it was bigger than or equal to 5, then you run it up, then we have 0.0. But here we have 0.01 because we need to run it down, right? So the yearly increase in the temperature, 0.01. All right. By the way, the system, MyLabMath, give you immediate feedback, and also you have unlimited attempts. That is the good thing. But you know, coin has two sides. The other side is maybe because you have immediate feedback, you have unlimited attempts, you might develop a bad habit and you are not very careful when you enter the answer in the cell. So be aware of that. Be aware of that. Because when you go to the exams, you won't have any feedback until you finish the whole exam. And you will not have unlimited attempts either. You only have one attempt. So I would recommend or suggest when you practice the homework assignments in Pearson, you pretend I'm right now taking my exam. I only have one attempt for this specific question, right? So I won't enter anything until I'm pretty sure this answer is right, right? Yeah, I just concerned because some students do very well in the homework assignments, but they don't do well in the exams. That might be due to the bad habit, right? Very good. That's the first part. Now let's look at the second part. The second part is about the modeling. A mathematical model that estimates the average global temperature T in degree Fahrenheit. X is the year after 1950. Doesn't that sound familiar? X is the years after 1950. So we need to find the equation of the line I have in a graph, right? So again, your equation is y equals mx plus b. But your y here, they use T because your y is temperature, so they use T. T equals mx plus b. Since T equals already given, you do not need to enter T equals. you need to enter this part in a cell. Okay, give you 1 minute. This should not take too long. Think about what should you enter in a cell. What is M? What is B? What should you enter in a cell? Perfect. You guys are awesome. Thank you, Cindy. Thank you, Charlie. That's correct. Very good. M value is the answer from part A, right? That's the slope, rise over run, 0.01. And they specifically tell you, use the answer from part A, right? To find this answer. So you use that from part A, times X plus B. B is the temperature in the initial year. We see 1950 as the initial year. So the temperature above the first bar, 56.94. Okay, so this is the thing you're supposed to enter in the cell. Let me do that. We should have 0.01x plus 56.94. 56.94. There we go. Right? Yeah, that's part B. Very good. Perfect. Thank you, Ashley. Yeah. One more part. Let's see part C. Part C is to predict. Prediction, in a sense, also kind of like a estimation, right? It's just you are estimating for a future value. Okay, part C, we are going to use the model from part B. Yeah, the model from part B. The model from part B is P equals 0.01x plus 56.94. So that's the model we got from part B. We're going to use that to estimate part C, to predict what? The average global temperature in 2025. Okay. Year 2025. I'll give you 2 minutes for this one. Give you 2 minutes for this one. How do we use the model to find the temperature in 2025? In order to know the temperature P, we need to know the value of X. What's the value of X, by the way? The value of X is 75, right? Yeah, exactly, 75. Because we see 1950. When in the year 1950, X equals 0. In the year of 1951, X equals 1. In the year of 2015, remember earlier, X equals 65, right? So in the year of 2025, that should be 75 years after 1950. So we should plug in X equals 75. right? And let me know your answer. What answer you should enter in the cell. Perfect. I'm going to enter this value. I'm going to copy Cindy's answer here. Copy Cindy's 57.69. Same with Ashlyn's. And paste here. Huh? Sometimes it let me paste. Hold on. It doesn't let me paste this time. Okay, I'll just type. 57.69. 57.69. Here we go, right? We got it. All right, we have 9 minutes. You are going to work on this problem. It is still about linear model. It is still a linear modeling problem, but this time the linear trend is going down. 1 second, let me find the problem. 18, no, 19. Yeah, this one. Sorry, number 20. So, number 20. We have two set of bars. Two sets of bars. First set, the orange color, trust in median percentage. Let me see the years. 2003, the percentage of people of the population who trust in media is 54%, over half. And over years, the percentage goes down. 2007 is 46%, 11 is 44%, by the year of 2019 is 42%. And the purple, let me just say that's the purple or grayish purple color is trust in government. In general, people trust in government is less people trust in government compared with trusting in media. And the trend is also going down. In 2003 is 36%, in 2019 17%. So this is a linear model problem as well, guys. It's just this linear trend is going down, okay? This linear trend is going down. Yeah, let's finish this problem. We only need to consider the government, okay? How do you know? Because I solved this problem many times. So if you read the problem thoroughly, you know we only need to concern the purple bars. So ignore the orange bar. The purple is the trust in government. We only need to concern trust in government. Part A, we need to find the yearly loss. Yearly loss in the percentage of trust in government. 2 minutes. Share your answer. This one is different because this one goes down. All right, this one goes down. So what difference that makes? You are right, Charlie. It is a negative slope. Perfect. That means later in part B, when you need to find the equation of the model, your M is negative in this case. However, in part A, let's look at the wording of the part A. Use the information to estimate the yearly loss. We are looking for yearly loss. It doesn't say yearly change, right? if it says yearly change, you would need to have the negative sign. But since it says yearly loss, you do not need enter the negative sign. You are going to have a positive number here. All right. The reason is because it's asking yearly loss. When people say how much money you lose in the casino, you say I lose -$5. That doesn't make any sense, right? You lost $5 because loss already indicates, already pointed out is losing. You're have less money, right? So you do not need to put a negative number in part A, but yes, you need a negative number in part B. Let's see, what's your answer? 36, 17, that's 19. 19 over 16 years. 19. It says round to the nearest tenth. Okay, let's do that together. So let's see how much we have lose in the trust in government over the 16 years, right? Yeah, obviously this is a 16 years from 2003 to 2019, that is 16 years. Let's see what's the total loss. Total loss. Beginning year 2003, we have 36%. By the year of 2019, we have 17%. That is 19%. Yeah, 19%, right? So over 16 years, the loss is 19%. So I would use 19 to divide by 16, right? And let's see what do I have divided 19 by 16. I have a 1.1875%. Okay, the percent, you don't have to enter the percent. The percent is already in the problem. Okay, so again, from 2003 to 2019, the percentage went down, gone down 19%. Over 16 years, 19%. Now, how many percent every year? Like averagely speaking, then you divide 19% by 16, right? You have this. But we need to round a number. Round it to the nearest tenth, so it means keep one decimal places. Keep one decimal places. So 8 is bigger than or equal to 5, so 1.2%. 1.2%. Do we have a close answer? Oh, perfect. Yes. Molly is correct, but you don't enter the percent anymore again because the question has a percent sign here, right? You only need to enter 1.2. You only need to enter 1.2. Right, guys? And how do you find the model? Your slope here from part A is going to be negative. I mentioned this earlier, right? Because the line goes down, so slope is negative. Negative 1.2 plus the percentage in the initial year, which is 36. Is that understandable? Without the negative line, the equation represents a straight line going up. So, which is not that case. So you really have to have the negative sign for the slope in the model. Okay? And then the B, the constant term, is the initial value of the percentage of the trust. Okay? And the part C, you just need to predict the trust in 2025. Same with the example we had and the temperature problem, global temperature problem. You need to find the value of X. Then you can plug in the model to predict the trust percentage trust in 2025. Yeah, okay, we ran out of time, so I will leave this for you to figure it out. Essential class, I just need to make it clear. If you are enrolled in the essential class as well, please meet me at 2:30 in a virtual classroom in your essential course shell, Blackboard course shell. If you are enrolled in a combo at 1 o'clock, you come to here. After this class at 2:30, you leave this virtual classroom and you go to the other virtual classroom. The other virtual classroom is in the essential Blackboard course shell. Alright guys, thank you so much for coming. You guys have a good weekend. If I don't see you again, work on your homework assignments. You should work on 1.1, 1.2 now. Email me if you have any questions. I'll see you on Monday. Yeah. Bye-bye. You're welcome, Mommy.
So we have Miss Betty.
Yes.
So we have class with you on Monday.
On Monday. Oh, my bad. You heard right. Not Monday. I'm sorry. I don't see you on Monday, guys.
Okay.
I'm sorry. I do not see
Okay,
you.
no, I'm just making sure. I'm just making sure.
You're
So,
right. I
not
forgot about
Monday.
it. Yeah, I do not see you on
Okay.
a holiday.
Right. But I see you in about
I
10
see
minutes.
you.
All right.
Yeah, I will see you on Wednesday. Okay, guys, I'll see you on Wednesday.
Yes.
Have a good long weekend. Bye-bye.
Yes, Miss Carr.
I don't even know.
Girl, I went in here and didn't get no kind of gas.
Oh, Lord.
Went in to do something else.
I don't even know how to turn this off. I don't even know how to sign out of this. This is what I don't like.
What are you doing?
It's on a whole different platform.